Good morning, everyone. We'll be starting in about half a minute. Uh, and A warm welcome to all the attendees on today's webinar. This is part of the series of the webinar on power system protection. Today's topic is protection of transmission line using overcurrent relays. Uh, this webinar will be hosted by uh, unknown faculty in this field. Uh, in the meantime, we hand it over the stage to the speaker. Stay tuned to the social media channels on Facebook, Instagram, Twitter, LinkedIn, and YouTube. All these webinars are recorded as a live feed and then available for future reference. In any time of the webinar, if you have any questions, feel free to put it into Q&A tab. We'll be happy to handle this at the end of the webinar. If the time constraint is there, we will ask the speaker to attend to all the questions and offline mode. Thank you very much, and the stage is all yours.
Good morning, everybody. We would be talking about transmission line protection, that is protection of transmission lines using overcurrent and earth fault relays. Transmission line can also be protected by distance relays and also by line differential relays. These webinars may probably follow, but today we'll be talking about overcurrent and earth fault relays. We start with a basic radial feeder, that is source only. There is only one source at one end and loads are at the other end. However, everyone might be knowing that our power system network of the state grid is highly complex, complicated. It is an interconnected network, and the protective schemes are going to be complicated. We will slowly enter into these complexities. This is the basic radial feeder. These figures which you see are typical. It is not necessary that all generators are 210 megawatt. 15.75 kV is the generation voltage, 210 megawatt. Power is stepped up, obviously, to say 220 kV, and then it is fed to 220 kV infinite bus. From there, many transmissions lines will go. One of the lines is going to 220 kV bus at the receiving substation. Line may be 100 kilometer long, 150 kilometer long, right? And then at receiving substation, I have assumed that it is stepped down to 66 kV. Not necessarily always 66. It may be stepped down to 132 kV if 132 kV happens to be the economic voltage of transmission. Then it will be further stepped down to intermediate substation. I mean, in the intermediate substation to 66 kV again. So 66 kV transmission line is going from that receiving substation. Many lines are emanating, and one of the transmission line is coming to a distribution substation where it is stepped down to 11 kV. 11 kV happens to be the distribution voltage. 11 kV transmission line terminates on a distribution transformer, or usually we call it PMT, pole mounted transformer. The voltage is stepped down to 415 volt and then fed to final consumer. I mean a very primitive, simple radial feeder. So we'll first see as to how such a radial system is protected. The pole mounted transformer, as you can see, is on the secondary side. There is a fuse, or in the modern times people use MCCB, that is molded case circuit breaker. The primary of the pole mounted transformer, that is for the protection of pole mounted transformer itself, DO fuse, that is dropout fuse, is used. That is we do not use any relays or anything, because pole mounted transformer is not that costly. The general rule for protection is you cannot spend more than 5 to 10% of the cost of equipment to be protected. That is, the cost of protective relaying system should not go beyond usually 10%. So DO fuse and the MCCB are enough to protect PMT. You cannot go for versatile relays. And obviously, when you use the relay, one cannot pass large current of transmission line through relay. So one needs CT, current transformer. If it's a voltage operated relay, then you need PT, and relay cannot interrupt the fault current. Therefore, one needs the circuit breaker. So circuit breaker, transducers, that is CT and PT, relay and relevant control circuit forms the protective relaying system. So that will obviously provide highly comprehensive protection and highly versatile protection system, but for PMT that is not required. For 11 kV feeder, one can go for a relay. So R3 as shown is the overcurrent and earth fault relay. This is a single line diagram. One line means 3 phases, and therefore R3 does not mean a single relay. R3 means there are 4 relays, 3 overcurrent relays, each for R, Y and B phases, and 1 earth fault relay or ground relay. So R3 is protecting 11 kV feeder. Now I have not shown any protection in distribution transformer or power transformer in receiving substation, because we are talking about transmission line protection. So R2 similarly is protecting 66 kV transmission line, and R1 is protecting 220 kV transmission line. If there is a fault in 415 volt distributor, then MCCB will clear the fault. It will isolate the faulty system from the remnant healthy system, and this is all what is known as protection. Protection means isolating the faulty part from the remnant of the healthy part. And more difficult is isolating minimum faulty part from the remnant of the healthy part. That is, you have to selectively isolate. And then another requirement, you have to isolate as fast as possible, very high speed. So both these requirements are going to contradict, and therefore the protective relaying system goes on becoming complicated. So if there is a fault in 415 volt distributor, MCCB will clear the fault. By chance, if MCCB fails, then there has to be backup, because if there can be a fault in line, there can be a fault in MCCB itself, there can be a fault in relay also, there can be a fault in circuit breaker also, there can be a fault in CT also. It may not faithfully transform. So one has to assume, one has to predict a fault in protective relaying system itself. So for fault in, if the MCCB does not clear the fault in 415 volt distributor, then R3 will give backup. This is known as remote backup. That is a protective relaying system away from this main system towards the source. MCCB will give primary protection, R3 will give backup protection. For fault in 11 kV feeder, same R3 offers primary protection and R2 offers backup protection. And similarly, for fault in 66 kV line, R2 will be acting as main protection and R1 will be secondary or backup protection. So this is how the protective system works. Now the main point is discrimination. If there is a fault in 11 kV feeder, R3 has to operate, but R2 is also going to sense that fault. R1 may not, but R2 will certainly sense a fault. So how R2 will understand that howsoever I am sensing, the fault is not within my region, fault is in 11 kV feeder, so I have to wait or I have to do something, and I should wait till R3 operates, and then only as a backup I have to operate. So that discrimination, how to carry out that discrimination. So to understand that, I have simplified the whole system. I have removed the transformer from the earlier figure. Section 1, section 2, section 3, we have to understand something like this, that section 1 is 220 kV line, section 2 is 66 kV line, section 3 is 11 kV line, something like that. And then through fuse there is a load. Now if there is a fault in section 3, R3 should operate, R2 should give backup. So R2 should understand that fault is not within my region. So how that discrimination between fault locations can be done? Discrimination can be done in 3 different ways. One, you can apply the instantaneous overcurrent relays. That is discrimination using current as a discriminating quantity. In that case, all these relays R1, R2 and R3 are instantaneous overcurrent relays. That means they will operate instantaneously once the current exceeds pickup. So there is only one setting, pickup setting. R1 is set to reach up to B. R1 will reach up to B. R2 reaches up to C and R3 reaches up to D. That means if there is a fault at B, R1 will operate. If there is a fault anywhere between line section AB, R1 will operate. Similarly, R2 will operate for fault in line section BC. But R1, R2, R3 will instantaneously operate. The principle is simple because current is going to reduce as the fault location goes farther from source. If the fault is at A, the current will be highest. If the fault is at bus B, the current will be lower. If the fault is at bus C, the current would be yet lower. So I use the current as a discriminating quantity. I use current to discriminate between fault location. Another principle is the use of definite time overcurrent relays. That is, there is not only current setting but time setting also. Pickup setting. If the current exceeds certain pickup value, the relay will start operating and it will really operate after the end of the set time. But that time is definite. That is, irrespective of the value of the current, the time of operation is constant. And the third kind, so obviously in this case, all the 3 relays, R1, R2 and R3 are now definite time overcurrent relays. Third kind is the use of inverse time overcurrent relays, or usually we call IDMT, inverse definite minimum time overcurrent relays. And these relays, inverse time overcurrent relays, are giving inverse characteristic. That is, the time of operation is inversely proportional to current. Lower the current, more is the time of operation. Higher the current, less is the time of operation. And exactly that is what we require, right? Because if the current is small, the equipment can withstand for more time, and we may wait for more time, and we must wait for more time because most of the faults, 85% of the faults are transient, and probably before the relay operates, fault might have vanished and you may not have to trip at all. But if the fault current is larger, it would be damaging, and therefore the relay should operate fast. Therefore, these relays R1, R2, R3 are IDMT relays. So these are the 3 main schemes to differentiate between fault location. Now, if we use instantaneous overcurrent relays, what are the difficulties? So basic 7 difficulties are there. Unrealistic accuracy of relays, right? First difficulty is this: relays have to be reliable. They need not be accurate. accuracy is not the main requirement of protective relays. Reliability. I do not mean that the relays may be badly accurate or inaccurate, but the accuracy standard up to 5% or even in certain cases up to 10% are allowed. So what does that mean? That if this relay R1 is set to reach up to B, that is set to reach up to 100 kilometer length, it may make a mistake of 10% or 5%. That means relay may operate for 110 kilometer. So that is wrong, because 110 kilometers is beyond B, for which R2 will also operate, R1 will also operate. That is not good, because from B, it is not only one line which is there. There are many lines which are not shown. So all lines will unnecessarily go to dark. If it minus 10%, if instead of 100 kilometer plus 10%, it is minus 10%, then it would protect only up to 90 kilometer, and then remnant 10 kilometer is blind. No one is protecting remnant 10 kilometer. Unrealistic accuracy. ZS by ZL ratio, this is the another problem. So for this, let us define ZS. Impedance from source up to relaying point is ZS, and from relaying point up to fault is ZL. Now if this ZS by ZL ratio is large, then fault current IF is equal to E upon ZS plus ZL, obviously, right? Now if ZS by ZL is large, you can forget ZL with reference to ZS, and then fault current is E upon ZS, which is constant. So fault current does not differ much or insignificantly differs with reference to fault location, and this is using only current as a differentiating principle, current as a differentiating quantity, discriminating quantity. Therefore, the ZS by ZL ratio, if ZS by ZL ratio is large, instantaneous overcurrent relays are highly prone to that, and they cannot be used. Therefore, this kind of discrimination cannot be used. Third very important thing is thermal withstand capability. All equipment can withstand fault current for certain time. Usually people specify 1 second or 3 seconds. So if they are going to withstand for certain time, why to operate the relay just in 3 cycles? Because instantaneous overcurrent relays will operate within maximum 3 cycles. Better time is 1 cycle nowadays. The relays are available which operate up to 1 cycle. Even lower time is possible. Accuracy will be lost in numerical relays. Half cycle algorithm is there. 3 sample algorithm is also there. So within 3 milliseconds, the fault can be sensed or identified. But then you are not taking advantage of thermal withstand capability of electrical equipment. Fourth is, as thermal withstand capacity, there is a transient stability limit. When fault occurs, generators are going to fall out of step. But generators can work asynchronously for certain time, and if the fault is cleared by that time, then generators will regain synchronism if transient stability limit is not crossed. Therefore, you have to wait till the transient stability limit is working. So which we are not waiting for in case of instantaneous overcurrent. Another very important disadvantage is no backup. R1 is reaching only up to B. Therefore, if the fault is beyond R2 and if R2 fails, R1 is not going to give backup. This is very important difficulty. Sixth difficulty is transient overage. Right? What is transient overage? Immediately after occurrence of the fault, because of inductance of the system, the fault current is like this. It's not necessarily that it will always be like this. It depends upon at what instant of voltage the fault has occurred. The worst instant is if the fault occurs at V equal to 0. Then there will be the worst asymmetry. So current is asymmetric. It is the sinusoidal current superimposed on exponentially decaying DC offset, as it is known as. It is not obviously DC, but it decays after about 15 to 20 cycles, not as it is shown in the figure, because it is difficult to show for me on the screen, to wait for 15 to 20 cycles. So if it decays after 15, 20, 30 cycles, that depends upon XL by R ratio. So if it decays very late, then during first 2-3 cycles, it is more or less constant. Therefore, it is named as DC offset. So the current seen by the relay, as you can see, the first peak or second peak is higher than the real steady state current. Therefore, relay sees more current than what actually it is. Otherwise speaking, relay feels that the fault is nearer. More current means the fault is nearer. Fault is nearer to the source. So fault, so to say, fault has occurred beyond B. Fault has occurred beyond bus B. But relay R1 feels that it is before B. This is known as overreaching. Relay sees the fault nearer than where actually it is. Therefore, it is known as overreaching of the relay. But this overreaching is transient. After the current becomes symmetrical, overreaching is not going to be there. So all time delayed relays do not suffer from the difficulty of transient overreach. Only instantaneous overcurrent relays suffer from the difficulty of transient overreach. Therefore, the next problem is transient overreach. And the last problem is type of fault. Type of fault means I am telling that R1 should reach up to bus B or R2 should reach up to C, but for which fault? You see, there are 10 different kinds of fault, or roughly speaking, line to ground, double line to ground, double line and triple line. So for which fault you want the relay to reach? And currents for different faults, the current magnitudes for different faults are different. So it is not possible to make the relay to reach for only one kind of fault, and therefore instantaneous overcurrent relays alone cannot be used. However, it is not so that they are not used. Instantaneous overcurrent relays are used in conjunction with time delayed relays, and in that case, I will make R1 to reach up to 80% of line section AB, assuming that the relay will overreach by 20%. If the relay manufacturer says that my relay overreaches by 10% only, then you can make the relay R1 to reach up to 90%. But R1 is made to reach up to 80 or 90% of line section AB for 3-phase fault there, because 3-phase fault current is highest. For 3-phase fault at 80% of AB with maximum generation. Once again, because generator is not one as it is shown, there are many generators in the system, right? So the full statement is like this: R1 reaches for triple line fault at 80 to 90% of line section AB with maximum generation. So that is how I set the instantaneous overcurrent relay. But to solve these difficulties, I go for the another kind of discrimination, that is time discrimination. I use definite time overcurrent relays. Now, current is not a discriminating quantity. Time is a discriminating quantity. Relay R3 operates after end of time T3. R2 operates after end of time T2, and R1 operates at the end of time T1. So what happens is, and now R2 is reaching up to D. Pickup is set for reaching up to D. So what is the reaching? R2 should reach for double line fault at D with minimum generation for phase relays, and for line to ground fault at D for ground relays with minimum generation. So it will reach up to D. It may go beyond D, I don't mind. So R2 is also sensing, R3 is also sensing any fault in line section CD. R3 will operate after end of time T2. If R3 or breaker or anything fails, that means not only R3, any item may fail, R2 will give backup after time delay T2, and R1 will operate after time delay T1. R1 reaches up to bus C, right? For pickup, it reaches up to C. So this is how, if one decides, then backup is also given and the protection is also there. All disadvantages which we have seen, right? Unrealistic accuracy, ZS by ZL ratio, thermal withstand. We are waiting now, so there is no question of thermal withstand capacity. Transient stability limit, backup is there. Transient overreach will not be there in time delayed relays. Type of fault I am taking care of, right? Because I am making it to reach for minimum fault. So maximum fault, obviously it will operate. So all problems are sorted out, but the biggest problem, very big problem, a very serious problem, R1 operates at the end of time T1. If there is a fault in line section AB, then very large time of operation is there. The fault is worst because faults near the source are worst. They are highly damaging, for which I am taking most time. So worst fault is cleared the slowest, and therefore definite time overcurrent relays can also not be used. They can also not be applied, and what can be applied is the inverse time overcurrent relays. R1, R2, R3 are now IDMT relays. My all problems are sorted out. Right? You can see with reference to definite time overcurrent relays how what time advantage I am getting. This shaded area shows the time advantage. Right? So R1 operates faster also, and yet also discriminatively. There is a discriminative time margin TD. So I have to maintain that discriminative time margin TD. What is the value of that discriminative time margin TD? That is variable. Variable means people are using different values in research papers and with reference to different kinds of relays, better relays, more accurate relays, better breakers, etc. But how to arrive at or how to calculate that time discriminative margin TD, that cannot be talked today in short discussion of about 1 hour, because this transmission line protection by overcurrent and earth fault relays is a 10-hourly business. Some 8 to 10 hours are required. We are just introducing, but all these details are given in module 3 of power system protection, which is uploaded on the app Idmt, and Idmt can be downloaded from Play Store, and you can very well see all details, complete details of transmission line protection by overcurrent and earth fault relays. You can also see that you can attach an instantaneous unit. So for severe faults, the faster operation is possible. So number 1 is shown that with IDMT relays are used in conjunction with high set units. So because we are using IDMT relays, we will talk about the rules of setting, but as I told, it is not possible to cover the rules in this session of 1 hour. But what you have to set is flux setting and time setting. These are phase relays and there are ground relays. Phase relays means relays that operate only for phase faults. That means the relays that operate for faults not involving ground. And ground relays are different. Construction wise they are same, but their setting philosophy is different. Setting philosophy of phase relays and ground relays are different. There are 2 main setting, flux setting and time setting. As such, if you go for numerical relays, there are 17 different types of setting, and one has to configure that numerical relay for the requirement of the user. Once again, everything cannot be talked, but all details are available in module 3. So what are the problems in application of normal inverse IDMT relays? First problem, as we have seen, ZS by ZL ratio. If ZS by ZL ratio is very large, normal inverse relays cannot be applied. So ZS by ZL ratio will be usually large in end section feeders. So ZS is source to relay for R3, source to relay is very large. So ZS by ZL ratio for R3 is very large. So what happens is, these are the 3 different characteristics shown together. Number 1 is the normal inverse characteristic. With normal inverse characteristic, if the current is differing by a small amount, right? So to say, you see, if there is a fault at F1 and F2, F1 means just after R3 and F2 means at the end of the feeder. So time of operation should differ by large amount. That is what I require. But because ZS by ZL ratio is large, time does not differ by a large amount because current insignificantly differs. Therefore, time difference is just 707 second for two different currents, right? But if you use very inverse characteristic, which is a steeper one, number 2, then time difference is 2 seconds. And if you use yet steeper characteristic, extremely inverse, then time difference is 2 seconds for same two different currents, same difference between two currents. The fault locations are the same, right? F1 and F2. Extremely inverse gives me better discrimination. Another advantage, R3 has to be graded with the fuse or MCCB, and R3 best matches that extremely inverse characteristic. If I use, then it best matches with the fuse characteristic number 4 or FCCB characteristic, right? And therefore the end section feeder would be better if it is protected by extremely inverse relay. The another problem is varying generating conditions, right? At night time the load is less, therefore you may trip some of the generators. Say there are 5 generators and you may trip 2 or 3 generators, only 2 are working because at night time the load is less. Obviously thermal power plant cannot be tripped like a switch, but if there is a gas turbine power plant, diesel power plant, they can be tripped very fast, right? 10 minutes is the time of starting and stopping, or even lower for many small generators. So you will be tripping those generators. When you trip, the rated current also will be less, fault current also will be less. And the worst case is the worst of all, and that is also possible. Protection engineer has always to think of the worst possibility, and worst possibility is fault current with minimum generation. That means number of generators connected are least. Fault current with minimum generation is less than load current with maximum generation. Then you can just not set the simple overcurrent relays. And what you should do is you have to use overcurrent relay in conjunction with under voltage relay 27, right? And the wiring diagram is like this. You have to set relay 51, that is overcurrent relay, for minimum fault current with minimum generation, right? So for rated current, which is higher than minimum fault current, 51 will operate, but breaker should not trip because it is a rated current. But when the current is normal, voltage is also normal, therefore under voltage unit is energized, because under voltage unit will remain energized if the voltage is normal. It will de-energize if the voltage collapses below 70%. So in the figure, it is an international norm that in drawing you have to show all relays in de-energized condition. So you have to read like this, that under normal condition 51 is operated but 27 is open, and therefore 86 is not energized. Breaker does not trip as per requirement, but if there is a fault, 51 will also operate and 27 will de-energize, energizing 86. Final tripping juice will be given. So this is all about the overcurrent relays. If we go to the ground relays, there are 3 methods of connections which we'll be seeing in the next slide, right? Philosophy of setting the ground relays is altogether different. There are many other considerations when we go for ground relays. Ground relay connected in residual circuit of 3-line CTs on delta side does not sense the fault on ground fault on star side, L to G fault on star side. So ground relay on primary side, delta side of a delta star transformer, and most of the transformers are delta star connected. You know the reason, right? Delta star connection avoids the or filters out third harmonic. So third harmonic filtering is very necessary. Many of our loads nowadays, when we are talking about the thyristorized controlled induction motor drives in large industries, we talk about the UPS, that is power supply that we are using for computers, and many other things. They are all non-linear loads generating large amount of harmonics. If those harmonics are transferred to generator, then generators are damaged, right? And even transformers are damaged for harmonics, because iron losses will be large. So to filter out, you are connecting delta star, but the problem is then ground relay on delta is blind for L2G fault on star. So these are the difficulties. Solution of all these difficulties cannot be discussed in such a short session, right? And you have to refer to our module 3 of Idmt, power system protection, which is already uploaded. One way of connecting the ground relay is like this. 64 is ground relay. It is connected in residual circuit of 3-line series. IR plus IY plus IB under normal condition is 0. So no current is passing through 64. 64 will not operate. IR plus IY plus IB is 0 even for double line fault or for triple line fault also. So 64 gives protection only in two cases, LG and double line to ground fault. Right. Another way is if you got a star point available in secondary of transformer, if the star point is available, then you have to connect the relay 64 in neutral CT that's provided, right? So once again, neutral current will pass only in case of L2G or double line to ground fault. So it protects only in these two cases. Third way is to use CBCT, that is core balance CT. The core encircles all the three phases, right? Core is encircling all the three phases. So because IR plus IY plus IB is 0 under normal condition, there is no flux induced and no juice passing through 64. 64 will get a juice only in case of line to ground or double line to ground fault, right? But the problem is you can use CBCT generally in case of cables only, because overhead lines, the distance between RY, YB, say for 66 kV line is of the order of 1.5 meter. For higher voltage, it is yet larger, and you cannot have a core diameter of the order of 3 meter or 10 meter. It is not technically feasible. Otherwise also there will be problems of leakage fluxes, right? So it can be used only in cables. So this kind of connection which is shown can be used usually for indoor switch gears, that is 6.6 kV and 11 kV, which are usually indoor. So ground fault connections can be like this. The details about how to set the relays, right? What are the methods of setting relays, how to coordinate the relays, how to grade the relays, all these things can be cannot be taught right now. And the another thing is we cannot solve the numericals also. If the time is there, 8 or 10 hours of time if we take, then we can solve certain numericals, certain examples to show as to how the setting is done. But all these things are given at length in module 3. Directional overcurrent protection, that is, most of the networks in our system are interconnected, right? Therefore, normal overcurrent relays which we have discussed will fail to provide foolproof protection. It can be used, normal overcurrent relays, only in radial system that we have talked about. So where do we need directional protection? Say this radial system which we have discussed, but now radial feeder fed from both ends, G1 and G2, it is fed from both ends. So in this case, one can see that there are relays R1, R2, R3, R4. Now this feeder can be divided in two parts. Forget G2, G1 on one side and load at D on another side. Then you can see that my last relay is R5, R3 is going to back up R5 and R1 is going to back up R3. If I see from reverse, that is from D side, then R2 is last relay, R4 is backing up. So it is like this. I can divide the radial system fed from both ends like this. But then my time of operation are like this. R3 operates after 0.1 second, R2 after 0.35 second and R1 after 0.6 second. I have assumed 0.25 second as discriminative time margin. But this creates a problem. You can see if there is a fault at F2, then my requirement is R3 and R4 should operate. But how does the fault current pass? Fault current is passing from AB to F2 and DC to F2. And in that fault path, R2 is operating within 0.1 second. R5 also is operating within 0.1 second faster than R3 and R4. Therefore, R2 and R5 will trip. That is wrong because all loads fed from B and C are disconnected. Therefore, it is a must that R2 and R5 should not operate, and therefore I need adding one more sense, directional sense. That is the direction of current with reference to voltage. So the relay is going to be fed by PT and CT both. It measures the angle between voltage and current. If the angle between voltage and current is less than 90 degree, then only the operative juice is available. So operative directions are shown by arrowheads. So for relay to operate, two conditions it must fulfill. The direction should be correct and current should be higher than plug setting or pickup setting of the relay. If you do so, then the relay will operate correctly and will give a correct protection. R1 and R6 need not be directional. They are bidirectional relays because current never reverses from these relays. So this is one more system where you would need directional feature. Parallel feeders. Most of the feeders in system are parallel because I have got a row of transmission towers, and on that two feeders are running, RYB on one side, RYB on another side. So I am being able to transmit double the power from one CT to another CT. But here the problem is if there is a fault at F1, current is going to pass from A to F1, one path, another path CDBF1. For path CDBF1, R2 will also operate and R4 will also operate. My problem is if R2 and R4 both operate, then my problem is what? That R4 will disconnect section CD where there is no fault because fault is at F1. So R4 should be operated later, but I cannot do that because if there is a fault at F2, then R2 should operate later than R4. So that is just not possible. So R2 and R4, plug setting and time setting are usually same, but they are given directional sense. Now for fault at F1, because current direction is CDBF1, which is reverse for R4. So R4 will not operate and R2 will correctly operate. R3 gives backup to R2, remote backup. If R2 fails, then R3 will give backup. If R4 fails, then R1 will give backup. Another very usual system in a distribution network is ring network like this. The generator is only on one bus, right? So here also you can see that R1 and R2 may be bidirectional, but R8, R7, R6, R5, R3, R4 all have to be directional, right? Cascaded parallel feeder fed from one end. So here also the directional sense are given. So these are the few examples of the possible networks, right? Possible networks which are used in the system. Networks can be yet more complicated, and the relay setting is also going to be more and more complicated. These are only 4 lines and 3 buses, but say in Gujarat system, there may be 50 buses and 100 transmission lines and 200 relays. So in that case, coordinating and grading the overcurrent relays is very difficult, and one cannot do manual calculation. One has to rather go for certain algorithms, computer algorithms, which will, because many iterations will be required, iterative calculation is required, and for that yet many people are doing research work. Yet even then, with all that, it is so often happening that at certain fault location, some primary relay does not operate, nor the backup relay operates, and some third relay which is not related will operate. This is known as sympathy trip, and people in research work are trying to reduce that sympathy trips. This is the way in which the directional overcurrent relay is connected. Current coils, voltage coils. Current in earth fault relay is fed by residual connection of 3 line CDs, and voltage also residual connection of 3 PTs. So you have to connect the relay across open delta of delta Y PT connection as shown, right? So this is the exact connection pattern for directional overcurrent relays. Having talked so much, I would just give a cursory remark to specifications of overcurrent and earth fault relays. If you want to procure the relays for your application, what are the specifications? How you will specify? How you will decide the specifications, and how you will calculate different specification items? My friend, these things are given in module 3 of the power system protection, which is already uploaded on Idmt. I do not have time to cover this. Then now very modern numerical overcurrent relays are available, and they are addressing many of the problems of protection. Protection is highly selective and yet much more faster than the earlier electromagnetic or static relays. Really speaking, electromagnetic relays are now not manufactured by any manufacturer and mostly not used anywhere. If at all they are used, people are slowly retrofitting using numerical relays. The details of these facilities cannot be given here. I will just read out. Self-diagnostics, that is, relay sees its fault. You have not to periodically test the relay. If there is something wrong with hardware and software of the relay, it will announce the kind of fault on the display window. All numerical relays have the display window, so it will announce. So because of this, the relays are much more reliable and availability of the power system increases. And if the availability increases, the electricity company will earn more. Availability of many mathematical functions, which is very difficult in electromagnetic relays and probably in certain cases just impossible. That is differentiation, summation, subtraction, integration, filtering of negative sequence and zero sequence current, filtering of harmonics. Many such mathematical functions and logics are there in the modern numerical relays. Most important thing, group settings. You see, in our system is highly dynamic. In a 50 bus system, 100 lines are there. If one line trips, then the current flowing through other lines, remaining healthy lines, are going to differ. The current distribution P plus JQ, as you are calculating, by many Newton-Raphson and this and that, and many methods you might be using. So P plus JQ is changing. Current flowing through each line is changing. Some another line trips, current is now different. So the protective relays have to adapt with the new condition of the power system, and that was just not possible in older relays because there was only single setting. As good as 6 settings are available in modern numerical relays. Fault storage. Fault current is shown by the relay. What was the value of the fault current? At what time the fault current occurred? And within what time the relay operated, right? What was the value of DC offset in that fault current? What was the value of subharmonic and superharmonics in that fault current? Complete fault wave shape is also shown by the most modern numerical relays, and not single. In most modern numerical relays, as good as some 60 last fault records are available, and more than 500 events are recorded. Any event that occurs in the system, that is recorded in event recording. So it is very useful facility because you can do analysis, and much more important is because you know the fault current, you know the location of the fault current, which was just not possible. The fault occurred in line section AB. 100 kilometer long fault has occurred, but whether the fault is at 50 kilometers, 75, 10, nobody knows. You have to patrol the line. In earlier days, the line staff used to patrol the line, and patrolling the line to check up the fault takes a long time. Whereas here the relay will tell you that it is 75 kilometers, not 75. It gives you the tower. The fault is on 300th tower. Right from start, on 301st tower the fault is there. So you go there, clear the fault. and give green signal to charge the line. Very important, very fast, right? The line is, power system is available very fast. Another important thing, metering, control and protection. Metering is there. Not only protection is much better than electromagnetic relays or static relays, but metering is there. Relay will measure current, voltage, power, reactive power, energy, power factor, negative sequence current, zero sequence current, many quantities are. You don't need separate meters. Control, it does many control functions. Circuit breaker failure protection, then trip circuit supervision, the interlocking, many control functions are available. Blocking some protection functions, reverse interlocking, many control functions are available. All these things I have described in my module 3 of power system protection. So these things. Condition monitoring of circuit breaker. If circuit breakers usually require maintenance after certain operation, the contacts are carbon layer is there, right? Because of arcing, there will be carbon layer, so that has to be cleaned, and spring adjustment is to be done, and many more things. So the relay remembers how many times the circuit breaker is operated, and it gives you a signal, it gives you an alarm, it gives you a reminder, as there is a reminder in your mobile calls that today is a birth date of your friend, and you wish him birth date. Similarly, relay will tell you as to whether the circuit breaker and similarly transformer is required to be. Starting function, blocking function, auto multiplying facility, that is the setting is multiplied by 2 times, 3 times. Such facilities are required in many functions. Switch on to fault, if the fault is already existing before the circuit breaker is made on, then you want to make the operation instantaneous. Load shedding can be done using df by dt, dv by dt function, and voltage memory in case of directional overcurrent relays. So these are the functions. I could not describe them in detail, right? So for today, I thank you all. I started at 10 or a little later than 10 and 10:54. So about 52 minutes I have completed. Now I hand over the floor to the organizers to handle the situation.
Thank you very much for a great webinar. We have time for a few question and answers. I will start reading them out. In the meantime, I'll request audience for voting the polls we will be displaying on the screen. Please participate in rating the webinars, and there are a few questions coming up on the polls. At the time of responding, there are also some coupon codes displayed on the screen, which is the limited time discount offers. These are the results. Thank you very much. And if we can have some response back on what is the most suited day for the such webinars, which suits the most to the targeted audience. Thank you very much for a great participation. This is proving to be a right day today as per the votes, and I still see votes coming up, so I'll just keep this poll for a moment, and then these are the results. Thank you for the participation. And then this is the time slot of the day today, Saturday, and then which time slot audience likes to get similar webinars and some other webinars on this. And I can see 9 a.m. to 11:30 a.m. the a preferred choice, and thanks for your wholehearted participation. I'll display the results in a moment. And the last poll for the day before we go on to the question answer is would you like exclusive sessions on industry practices and examples by experts, and that could be on the webinar platform, or that could be on the Zoom platform, or any of the online screen share platforms. Thank you very much. This is really appreciated. We really thank you for your honest opinions. I will go on to the question answer. There are few questions as we can take quickly before going to the end of the webinar. One of the question is the application of PLC in the switchgear and protection for different operation of relays and sensors.
PLC can be used, programmable logic controller can be used for, because the control circuits are becoming simpler if you use PLC. So as far as control circuit part is there, PLCs are good, but the programming part, if you see, then the most modern things which are used are the DSPs, digital signal processors, in most modern numerical relays. Yes, please.
The next question I'll try to read out for delta start TX, I mean transformer. If I'm not wrong, what will be the EF backup at delta if star EF failed?
Please speak little loudly.
For delta start TX or transformer, what will be the EF backup at delta if star EF failed?
Star side relay fails, then I think the question is, if star side relay fails, then how will the relay on delta respond? If it is a phase relay, that means if there is a triple line or double line fault, the delta side relay will give backup. But if there is line to ground fault on star side, then it is seen as double line fault on delta side. And if the value of that double line fault, if the ground fault has occurred on star side some 100 kilometer away, then fault current is so small that phase relays may not be able to sense. Then backup can be given by a relay provided in neutral circuit, as I have shown. Right? The relay, earth fault relay across neutral CT, that will give backup. But delta side ground relay cannot give backup. It just cannot give backup. Yes, please.
Thank you for this. This is another good question, sir. Can you please explain about XR ratio? What does it mean to us if we know the ratio?
X by R ratio, the inductive reactance to resistance. Just thumb rules, not exact, not exact calculation, just thumb rules. For large generators, very large, 210 megawatt, 120 megawatt, 660 megawatt, XL is roughly 50 times R. XL by R is about 50. So you can forget resistance. Resistance is not there. For large transformer also, more or less same order. XL by R is 50. XL by R for transmission line is variable. For 11 kV line, these are all thumb rules. Exact data you have to ask from transmission line designer. I am not giving final values. 11 kV lines, XL is equal to R. 66 kV lines, XL is about 3 times R. 2.5 to 3 times R. For 132 kV lines, XL is roughly 5 times R. For 220 kV lines, XL is more than 6 times R. And for 400 kV, XL is about 8 times R. Obviously, for 765, it will be obviously more than 8. Up to 400 kV, XL is 8 times R. And if you do 10 inverse 8 by 1, then the angle, I think, must be turning out to be some 83 degree or 87 degree or so. So for all practical purposes, when fault occurs, our power factors are very poor, very bad. Yes, please.
Thank you. The next question is, do we need to use same discriminating element for all relays in a system from source to load?
Discriminative?
Do we need to use same discriminating element for all relays in a system from source to load?
Yes, from source to load. You will have to discriminate between fault locations. You will have to discriminate with reference to magnetizing inrush and normal current. You will have to discriminate with reference to starting current of induction motor and normal current, or starting current and fault current, magnetizing current and fault current. One has to discriminate between field failure and reverse power. One will have to discriminate between field failure and pole slipping. So discrimination is a must, and discrimination is done not only by single quantity. Based on requirement, it is done by different quantities. Say, magnetizing inrush and fault current in the power transformer are discriminated by using second harmonic content in the differential current. So you will have to measure the second harmonic content. So discriminating quantity will go on differing, and will go on becoming quite complex when we discuss further. Yes, please.
There are few comments we would like speaker to know. There are people commenting on happy to listen again your lecture and learning something new on this thing. Thanks, audience, for mentioning this. This is really welcoming to Team Idmt and of course Professor Oza. This is proving out to be a good turnout and good participation from audiences as well as uh, all the professional people out there. There are few questions. Please tell us about 1.3 second NI versus 3.0 second NI settings of IDMT relays.
There are two kinds of relays available. There is one is a 3-second relay, that is the time of operation of IDMT relay, inverse time overcurrent relay, in the normal inverse characteristic is 3 seconds at 10 times the setting. That means at PSM equal to 10, the time of operation is 3 seconds. But if you want faster operation, no doubt you can do it by using TMS also. But if you want yet faster operation, the another kind of relay is at PSM equal to 10, the time of operation is 1.3 seconds. So two kinds of relays, 1.3 second and 3 seconds, that is time of operation at PSM equal to 10, are available in the market. Yes, please.
Before we go on to the next question, just for the awareness for the audience, there are multiple modules, including good modules on power system protection are available as per the previous slide. There are various topics covered on Idmt, which is the AI-powered online learning platform and a framework for knowledge delivery. Do visit us, do subscribe to our channels and social media pages for updates. The next question is how TMS and PS of IDMT relays are updated adaptively for varying network conditions.
Good question. As I told, it would be difficult to describe, giving to you the figures, because I was not ready to discuss the figures in such a short time. But to answer fast, I can say that whenever the power system conditions differ, there is going to be some switching, right? Because some line trips means that breaker has tripped. Now, once the breaker trips, the auxiliary switch of that breaker is available to us, because breaker has 3 main power contacts plus 8 NO and 8 NC auxiliary switches are there in the breaker. That is, they are just mechanical switches. NO switches means when the breaker closes, that switch will close, and when breaker opens, it will open. So NO and NC switches you can use in the control circuit, and you can give binary input to a numerical relay. When you give binary input, and if you have properly configured the binary input, it will change its setting to another one based on that tripping, that is switching available. So one must have some switching sense available, and that will always be available from the system, because when something is switched off or switched on, then only you would like to change the settings. So it can be changed from the manual, from the closure of the circuit breaker switch using binary inputs. As good as 16 binary inputs and as good as 16 binary outputs are available in modern numerical relays. Please, I think I am trying to satisfy your question.
Yes, there is some announcement next Saturday. We have another webinar from Professor Rosa on Introduction to Electrical Power Generation. I request audience to stay tuned to our LinkedIn pages and all social media pages, LinkedIn, Twitter, Facebook, as well as YouTube, where we'll be announcing. So every Saturday we have uh, most of the power system protection series available, as well as we will have other subjects as well. So stay tuned to the channels. I'll just take few more questions. Is neutral conductor is connected at a star of alternative in power generating station with three phases?
Neutral of the
Stator of alternator in power generating station.
yes, neutral of the stator of the generator in power stations is not connected effectively. That is, it is not connected. That is, solid grounding is not there. It is grounded through a very large impedance. Say for 210 megawatt generator, the grounding impedance is of the order of some roughly 4,000 ohms. That is a very large impedance. For earth fault at the terminal of the generator, the earth fault current is reduced to 2 amperes. I am talking on primary side, 2 amperes. 10,000 by 5 CTs is hardly 1 milliampere on secondary side. So practically negligible current which will not do any damage. So the generators are high impedance grounded. I think this is what you wanted to know.
Thanks for that answer. Why should we prefer overcurrent relays over distance relays? That's, I think, a good question.
One should not rather prefer overcurrent relays over a distance relays. I think probably it's a reverse question, or if I don't make a mistake, we should use distance relays preferably over overcurrent relays, because overcurrent relays have many problems, many limitations. So as has been announced by Mr. Apurva Oza, we will be having a session on distance protection also. So at that time, we will be discussing as to what are the limitations of overcurrent relays. But yet, you see, overcurrent relays are used because once again, it's a question of economy. Distance protection scheme are much costlier, some 3 to 4 times costlier than overcurrent protection schemes. And therefore, overcurrent protection is limited to 11 kV and 66 kV lines. 132 kV and onwards, distance relays are preferred. However, overcurrent and earth fault is used as a backup up to 765 kV, no doubt. It's not so that overcurrent is not used, but main protection beyond 132 kV is distance protection, because distance protection overcomes many difficulties, many limitations of overcurrent is not preferred, distance is preferred. Yes, my friends.
Thank you. There is another question. Just a moment. From R1 to R3, are we using the same curve? If R3 is Ni, then R2, R1 also Ni?
Not necessarily. R1 can be normal inverse, R2 can be very inverse, and R3 can be extremely inverse. You have to properly grade them. That is, coordination has to be properly done, and that one must know. Coordination can be done manually if it is a short, it's a radial system as we have done. Otherwise, nowadays people are using softwares like ETAP. So there will be a plot on the software. Plot will be available, and using that plot, you can find out what should be the plug setting, time setting, etc. Go on changing that, and the software will suggest you what should be the plug setting and time multiplier setting of R1, R2, and R3. R1, R2, and R3 need not be same curve. They can be different curves. Yes, please.
Can we use extremely inverse curve for 11 kV line protection?
Yes, by all means. We can use extremely inverse curve for 11 kV. That would be better also, because after 11 kV there is going to be a fuse or MCCB, and extremely inverse best matches with the and in the numerical system the best advantage is, if you think that you want to use extremely inverse relay, the same relay, one relay offers some 17 different characteristics: normal inverse, very inverse, extremely inverse, long time inverse, IT equal to constant, I square T equal to constant, many more characteristics, not only as per uh, so to say the International Electrotechnical Commission IEC standards, but they offer as per NC standards also, and according to the other standards like German and other standards, they do offer different characteristic, and you can change the characteristic of the same relay. You have not to buy another relay. In single relay there are many characteristics. So now today you are feeling that R3 should be extremely inverse, but after 2 years you feel that R3 should be very inverse. You can change the configuration. Yes, please.
There is a question, if I can read it very correctly. It says using ZS over ZI or XS over XI is same for discrimination. I hope
ZS
I
over
have
ZL.
read the right question. Yes,
ZS by ZL,
Z,
that is
that's correct. ZS by ZL or XS by XL.
XL. ZS by ZL can be used for discrimination. That is the question.
So ZS over ZI or XS by XS over XI is same for discrimination.
Actually, rightly speaking, ZS we are telling for the sake of telling. For very high voltage lines like 220 kV and 400 kV and further, you can forget about resistance, and whether you say ZS by ZL or XS by XL practically means the same thing. It does not differ. The value will not differ, because resistance is a very negligible part. Yes, please.
There's a good question. I think that will take a lot of time, but you can briefly touch on this, and then we can take it offline. The question is there any new research in power system production nowadays?
That is a good question. Many researches are going on, no doubt. The relays based on traveling waves are being thought of. No doubt, I heard, I asked somebody, and I heard that some of the manufacturers have started offering the relays based on traveling waves. Another thing, the slowly after about few years, people will find out the relays based on artificial intelligence and fuzzy logics, because you see, artificial intelligence easily caters to the adaptive requirement. If you train your AI, it will change the relay setting according to a requirement. So not only 6 settings, but innumerable number of settings will be available as per your requirement using AI. So the protective relays using AI and fuzzy logic may probably come up in the next days, in the next era. Yes, please.
I think we'll take one last question, and then we can give it a conclusion. Can we use a reverse blocking feature if transformers are operating in parallel?
Reverse blocking feature for transformer
In parallel.
in parallel. Reverse blocking principle is actually, if there is a relay, one relay R1 is backing up R2. So once R2 senses the fault, it will give signal backup, blocking signal to the backup relay towards the source. If 2 transformers are in parallel, then there will be 2 backup relays, one R2 and 2 R1, right? So you have to give reverse interlock to 2 relays. It is quite possible. That is also possible to give blocking signal to two relays is also possible, because nowadays there may be more than two starting relays you can use, because people are offering as many as 16 binary outputs. From 16, 4 may be power outputs and remaining 12 may be signal outputs. All signal outputs can be used for reverse blocking or reverse interlocking. Yes, please.
Uh, I think there's one good question. I'll take it. But before that, I'll request audience to just note down the coupon codes. This will be sent out on an email as well. Should you, if you are interested, I can see one of the question as well, mentioning, are there any books written by the speaker? Yes, there are quite a few books written by Professor Bhuvanesh Oza, as well as now we are hosting all those modules and all those knowledge onto our app called Idmt, which is right now available on Google Play Store. And all these topics, such as malfunctioning of relay coordination and further interesting topics, are covered. We are launching every month a few modules on electrical power system protection by Bhuvanesh Oza. And I'll take the last question before concluding the webinar. This is for which application we can use distance protection. There is a case study in our plant. We are using distance protection for bus bar plus cable for just 1 kilometer length. What will be effectiveness of distance protection? Like to mention that we are using differential protection plus OC protection also.
If there is a short cable in your plant, if there is a short cable up to 1 or 2 or 3 kilometer long, or maybe 5 kilometer long, because cables I think should not be more than 5 kilometer in any given plant. Usually in that, the differential protection is the best. Distance one should not prefer, but the carrier aided distance is available, which is using line differential principle and distance principle both, because it gives an advantage of backup also. So one should better use carrier aided distance protection. Overcurrent protection can be used as a backup, but the differential protection scheme is the best. And if 5 kilometer distance is there, then differential is not at all costly. Even carrier is not required. One can use wire pilots also in this case. I mean, that is also quite possible. And very good schemes of wire pilot are available in the market. Yes, please.
I think we are running out of the slotted time for the webinars, where we've got few other webinars coming up as well. I sincerely thank all the participants for their wholehearted participation. Very good practical and very good questions, and the question and answer sessions. We really thank each and every participants for making up this morning on a weekend. And stay tuned to our social media channels. Please subscribe there, where all these webinars will be listed as a free view onto the YouTubes. And of course, on our app, there are some coupon codes. So please feel free to connect with us for any offers onto the modules other than power system protection as well, where we are launching few new modules, including cryptocurrencies and uh, some of the time management and stress management skills for industry professionals. Uh, we really thank Professor Rosa for this wonderful session, and thanking you once again. We can end this webinar in a few minutes. Thank you.